segment, don't we? We just added more to our context. Okay? So if we have 30 segments, we need 30 base bounds pairs. Right? We don't need a base bounds pair for the unused segment because it's unused. It's not part of my process anymore, is it? Okay? So I only need to have the information there for the segments that I'm currently using. Intel is the classic segmented architecture, although it's not used much anymore. There's a way of configuring your system, and XV6 does this so that we call it making segmentation a pass-through or invisible. So if you take a careful look at your code, you know the difference between segment and paging. You'll see that we never actually do segmented addresses in XV6, and that's because we did something to make them, in essence, go away. We might talk about that at the end of next week. So, some things that we need to think about. We need to give, whenever we bring something into memory, a piece of a process, we need to give it a chunk of memory. You know, unless we go through and inspect the entire ELF file and figure out what's the minimum amount they're going to need for the data section, okay, which is painful, takes a lot of time. So we're just going to say, hey, this is the segment size that seems to work for most processes when they start up. Okay. If I'm putting your process, putting your data segment into memory and there's not enough room, I'll just expand the segment, which means I may have to relocate you. But most processes, we want to set it up so that most processes, the default size works for everyone, which means we're still going to have some internal fragmentation, but it's going to be dramatically less than what we had before. Okay, just going to ignore that for a little bit because it turns out the external fragmentation is the really, really hard problem. So, address translation. Put this. Okay. So one of the things that we need to think about is when we do a translation, now that we have multiple segments, how are we going to identify which segment we're in? Okay. It turns out we're going to use a technique called bit stealing. All right. And this is used in communications protocols, all sorts of stuff. There's even one called bit stuffing in communications, particularly Ethernet, that's kind of interesting. So we're going to steal bits. So our architecture now, say it's a 16-bit architecture, we can generate 16-bit addresses. But we're going to steal pieces of that address space in order to create multiple segments. And we're going to steal the high bits. Does anybody know why we steal the high bits in this architecture? It's not obvious, okay, but it's worth thinking about. If on this particular segment specifier is 0, 1, remember I said we're only going to have 3 segments we cared about? So we need 2 bits, right? Okay. So it turns out then that if we're in segment 0, 1, the lowest offset into that segment is 0. The highest offset of that segment is all 1s, isn't it? And it turns out, if we keep this number fixed, all of these addresses are contiguous then, aren't they? So this is why we steal high order bits. So we break it up into chunks. Okay. Now, this offset corresponds to our maximum segment size. This is how we prevent you from accessing data outside of the biggest segment you can have. The translation process using the bounds register tells us whether or not you're accessing an address inside your segment that has not been allocated. Okay. Note on this that if we just have code, data, and stack, it turns out, and these are the numbers that are used under Intel, it turns out that the segment bits, which we call the selector, in this model we can't use 1, 1. Excuse me, we can't use 1, 0. Stack 0, 0, sorry. This is 1, 1. Sorry. The selector is 1, 1 for the stack. Okay? And that's because it corresponds to the unused space. So there's parts of our address space we can't use. The compiler has to know about it, and it has to say, hey, I'm not going to generate addresses to begin with 1, 0. So it's 0, 0, 0, 1, 1, 1. And if you think about that as being regions, anything that starts with 1, 1 is going to be at the far end of the address space, isn't it? And that's where we want the stack. Okay? We can grow them towards each other in this model, but they can't actually hit. They can't meet. When we run out of space on our heap or our stack, it means we've reached the maximum segment size in this model. Not that it's our own fault. Well, it is our own fault, but we've run out of segment space. Okay? So, the book talks about 2 different ways to calculate the addresses based on whether or not your addresses in your segment use grows up or down. Which segment's going to grow down? Stack. Which one's going to grow up? Heap. Which one's not going to grow? Code. It turns out that's a very useful thing to know. It will never change size. Okay. There are some languages that allow you to dynamically rewrite the code on the fly. Okay, we're not talking about those. I think there's only 1 or 2 that's still in use. So now what we've got is this is the segment selector. And remember, this is supposed to be 1, 1. As long as I got my pen somewhere, I should make this note. Fortunately, I'm one of those guys that never makes mistakes. You're all one of those people, right? I wish. Okay, so now what we're going to do is we have an example. In this example, we're going to have a 4K address space. 2 bits are selectors, so we have 12 bits left for the segment offset. 12 bits just happens to correspond to 4K. All right, and we're going to use 4K is going to be a common number we're going to use throughout our virtual memory discussions. So now that means the maximum segment size is 4K, because that's what we can represent in 12 bits. Bits 0 through 11, when they're all turned on, is going to be 2 to the 12th minus 1, isn't it? Okay, so that's how we can tell how big that is. Remember, 1K is 2 to the 10th. And that's the number I remember in order to make this type of calculation easier. All right? It's just 2-bit shifts or times 4, so it's 4 times 1K. It works out pretty fast. So now what I'd like everybody to do is to note this, okay? Because it turns out we have this thing where we say for these virtual addresses, virtual address decimal 100, virtual address decimal 4200, in base 10, what are the addresses in physical memory? I will point out that there's never been a time when I have not asked this type of question on an exam. It'd be good to practice now. So go ahead and figure it out. The book uses 2 formulas. This is the formula I use, and we'll talk about it when I work this example. How many people read this section of the book? We were hoping to read it before, maybe 4 weeks from now. Okay. I did mention that memory translation is hard, didn't I? until you practice it quite a bit, it's very, very tricky.
Is that -1 to the on?
-1 to the GN.
GN.
It's this thing right here.
Ah, beautiful. What does that stand for?
Grows negative.
Grows negative. Great.
When you read the book, you saw that this was gross positive. But it didn't have a gross negative. But it turns out for my formula to work, you need a gross negative, which it turns out is the inverse
Huh.
of this. Because the book gives you two different formulas for doing address translation and segmentation. And how many of you would really just rather remember one formula? Okay, so what I want to do now is I'm going to switch over to my tablet and let's go ahead and solve this problem, okay? So I can't prepare it, I wrote it down. Okay. How many, did people get this table written down? It would be very helpful if you did. Or if you have your computer. So what we're going to do now is we're going to note we have code. Come on. We have code, data, stack. Segment selectors are 0, 0, 1, 1, 1. Okay? Our base, and what we mean by base is just what's the value stored in the base register. Okay? Now the base register is very, very interesting in that it points to the start of the segment. Okay? This first example, that we're going to use it in a way that's intuitive. We're going to, when we get to the stack, talk about how that's not intuitive. And then we'll have to talk about what the offset means. Okay? So we have 32K, 34K. Hey, look at this. 32 and 34. Those things are, that says that the code segment's 2K, isn't it? But the maximum segment size is 4K. Okay. 28K. The current size, though, is 2K. So even though the maximum segment size appears that the code could grow into the heap, right, we're saying we're only currently using 2K. If we need to grow this, we need to see if there's any segment next to us. And if there is, we need to go find a hole someplace else. Which is fine, because all we're going to do is update the base register when we find the hole and set the bounds to the new value. Right?
Is that 28K correct, or is that supposed to be 38?
28K.
Is that not based off of the selector?
The base is physical memory.
Oh, right, okay, sorry.
The selector is part of the virtual address.
Yeah.
Do you see how it starts to get weird in a hurry?
Yeah.
Okay. So, 2K, we're going to say each of these is 2K. Now, The book talks about tracking which direction segments grow. Do they grow in a positive direction or a negative direction? Code, if it's going to grow, it would grow in a positive direction. The other way of saying that is that our offsets are, now let me back up. Let's leave that offsets out of this for now. So it says, hey, track grows positive. Okay. And it turns out that based on the grows positive field, the book tells you to use one formula or a different formula. Okay. I don't like multiple formulas, so it turns out if you track whether or not it grows negative, which is just the inverse of grows positive, right? Where 0 and 1 mean true or false, but we're going to use them as actual numbers. Okay. It turns out that the formula you can use is -1 times the maximum segment size. Whoops. Okay, we're going to take the -1
To the GN.
So, actually, let me back this up. I'm going to change this formula because I realized that -1 times grows negative times maximum segment size. My notes, I've had this wrong for like 2 years. Okay.
Work it away with.
No, any number raised to the 0 power is 1. And what we want to do is get rid of this term.
But that would make it 0 and
But the node is going to be 0 forever now.
I'm sorry?
At 0.
I can't hear you.
If GN is 0, say for code,
Yeah.
isn't the whole thing now 0?
Yes, that's what we want.
Okay.
We want the term to fall out if we grow positive. We'll see that in a second.
But he's saying the entire expression EA would just equal 0 all the time.
no, you're still adding stuff.
I haven't finished writing that formula yet. Plus offset. Okay. And this is where we have to think about what it means to be an offset. Offsets, signed or unsigned? I heard signed. How many people say signed? How many people say unsigned? How many people are hoping to see how this magic trick works? In order for it to be signed, we're going to have to take half of that bit space and turn it over to a signed bit, aren't we? Didn't we actually say that we couldn't generate negative addresses? So in order to have a bigger maximum segment size, we're going to make them unsigned. Okay. This means the following. And this is the part that messes most people up. Not in this example, but in the next one we're going to do. The offset is not relative to the base. Okay. All right. Our book doesn't talk about this. And as a result, it can be very confusing. The offset is relative to the lowest address in memory we can have for our segment. Now, if it turns out that if the segment grows positive, it turns out the base is the lowest address in the segment, isn't it? So it turns out if you grow positive, we want the formula to be base plus offset. So it turns out that if it grows positive, this guy falls out and goes to 0. When we see the stack though, okay, its offset has to be relative to the lowest possible address in its segment, but the base register points to the highest possible address in its segment, doesn't it? Because the bottom of the stack is at the top of memory. So it turns out that this becomes the formula in the book, base plus offset, for when you grows positive. And that's the formula they tell us in the book. It becomes the formula for stacks when you grow negative. Okay? So now, we have 100 base 10. What's the first thing I'm going to need to do with this?
Base 2.
Yeah, I want to put it in binary. Okay? And so we're going to subtract 64, right? Which is 2 to the 6. Which this is going to give us back, what, 26? 36. Okay? And we're going to subtract from this 32, which is 2 to the 5th. Okay, this is going to give us 4, which is 2 squared, right? And all the other bits are zeros, aren't they? Okay. So we have a 14-bit address space. 0, 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 13. So we have bits 0 through 13. Okay? And we're going to turn on bits 2. And 2, 3, 4, 5, and 6. 0, 1, 1. Okay. Now that's my virtual address.